Welcome to lecture 22. We have started our discussion on pressure measurements and we are talking about measurements of moderate pressures and high pressures. So, in the previous lecture we have talked about various types of manometers. In this lecture we will talk about piston type or deadweight pressure gauge, ring balance pressure gauge and bell type pressure gauge. Then we will take few numerical examples on manometers. So, let us first talk about deadweight pressure gauge. Look at this schematic for a deadweight pressure gauge. It consists of a vertical piston, then there is an adjusting piston and you have a reservoir. So, all are connected and then you attach a pressure gauge here. So, this deadweight pressure gauge or deadweight tester can be used to calibrate a pressure gauge. So, the steps for calibration of the pressure gauge using deadweight pressure gauge are as follows. Gauge is attached to stem B. Now, we place a suitable weight on the vertical piston. So, you select a suitable weight and place it on the vertical piston A. Move the adjusting piston C so that weight and piston are supported by oil and it is floating freely. So, the piston must be floating freely. Please note that the entire tubes are completely filled with oil. Now, when I place weight on this piston, the piston should be freely floating. It must not come down and support itself by this platform or the piston. So, it should be freely floating. At this stage, you record the gauge reading and the weight. So, look at the gauge reading and the weight. So, now you select another weight and place it on the vertical piston and see the gauge reading. So, repeat these steps in the increasing order of weights and then you can also have observations on decreasing order of weights. So, these are your known weights So, these are standards or primary standards. So, you know the pressure that is being applied. So, from the gauge reading, you can now calibrate this gauge by comparing its reading against the known standard. Let us now talk about ring balance manometer. Note that the deadweight pressure gauge as well as the ring balance manometers are the instruments where I am measuring pressure by balancing it against known force. A ring balance manometer is used to measure differential pressure. This is a schematic of a ring balance manometer. It consists of a tube with circular cross section. The tube may be made of plastics, the tube may be made of aluminum, metal, and so on and so forth. So, a tube is bent into a ring and is supported at the center by a pivot. The tubular chamber is divided into two parts by splitting, sealing and then filling with a suitable light liquid such as kerosene or paraffin oil for isolating the two pressures. This liquid is known as sealing liquid. So, you first take a tube maybe made of plastics or maybe made of say aluminum, bend it into a ring. This is supported at the center by a pivot. Now, let us cut the tube and two ends that are now created are sealed, and then inside I take a sealing liquid. Then I create two chambers, one chamber is this, another chamber is this. So, a ring which has a partition here, inside that I take sealing liquid. So, I basically create one chamber here, I create another chamber here. The liquid that I take inside is known as sealing liquid, and common sealing liquids are kerosene and paraffin oil. One can also take glycerin. These ends are connected to the pressure source which I am going to measure. So, I am going to measure differential pressure. So, I am connecting this to two different pressure sources P 1 and P 2. Now, when P 1 equal to P 2, that means the two ends are connected to the same pressure source, the tube will not experience any torque, the tube will show no movement. But if these two limbs are connected to two different pressure sources, or these two chambers are connected to two different pressure sources, then the ring balance manometer will experience a torque which will try to rotate the ring, and then there is a weight attached to the ring which will try to arrest that rotation. So, there will be a balance between these two opposing forces, and when balance is obtained, the rotation of the ring or the angular rotation of the ring, which is measured by an angle phi, becomes a measure of the differential pressure. So, when P 1 is equal to P 2, when P 1 is equal to P 2, the angular rotation will be 0, because the ring will show no rotation. But when P 1 is not equal to P 2, that means the ring balance is connected to two different pressure sources. There will be a net torque which will try to rotate the ring. Let this rotation be measured by angle phi. So, this phi is a measure of the differential pressure P 2 minus P 1. You can derive this equation which is P 1 minus P 2 equal to 2 W r sin phi divided by alpha into d, where alpha is the cross sectional area of the tube, W is the weight attached to the ring, r is the diameter, but which diameter? Please look at here, this diameter. You have attached the weight and then consider a circle like this. So, that diameter is r, sorry, that radius is r. Phi is the angle by which the tube has or the ring has rotated, and d is the ring diameter. D is the ring diameter. So, this is the d by 2. So, this equation can be written by analyzing the torque. Please look at this equation carefully. This equation does not include any term that is related to the property of the sealing liquid. So, what it means is the sealing liquid merely works to create two chambers for pressure applications. It does not play any role in the calibration of the instrument, because the property of sealing liquid does not appear in the working equation. So, if you change the sealing liquid, the working equation is nowhere going to be affected. The sealing liquid only creates two different chambers for applications of pressure. Now, let us talk about bell type manometer. So, we talked about deadweight tester or deadweight pressure gauge, also known as piston type pressure gauge. We talked about ring balance manometer, and now we are going to talk about bell type manometer. all these three instruments work on the principle that you balance the pressure against a known force. Bell type manometer consists of an inverted container which is immersed in a sealing liquid. So, this is the bell. First, let us consider this schematic. This is a bell type pressure gauge. So, it consists of a inverted bell. So, it is nothing but a container which is inverted, and it is inverted and immersed in a pool of sealing liquid. So, this is sealing liquid. Now, the bell is spring restricted. Now, look at here, you had a reservoir of sealing liquid, and then you have put an inverted bell, and then you are applying pressure inside the bell. So, you have created chambers like this. So, when you apply pressure inside, it will try to push the bell up. Of course, that will be restricted by the spring, and the displacement shown by the bell is noted as H. This displacement of the bell is a measure of this pressure. Note that when you invert this bell, in this reservoir, you create a chamber for application of pressures. So, inside that you apply the pressure which you are going to measure. There is application of, say, atmospheric pressure here, and these atmospheric pressures and these pressures are separated by the sealing liquid. So, the net displacement of the bell, which is measured by H, is basically a result of application of this pressure and the atmospheric pressure. So, this H will be a measure of the gauge pressure. So, bell type manometer consists of an inverted container immersed in a sealing liquid. Sealing liquid forms two chambers. The pressure to be measured is applied to the inside of the bell, the motion of which is opposed by a restricting spring, and the motion of the bell is a measure of the pressure that you are applying inside the bell. Now, the bell type manometers can also be used for measurement of differential pressures. Here, the bell type pressure gauge we use to measure gauge pressure. Now, let us look at this schematic which can measure differential pressure. We call it bell type differential pressure gauge. Now, if you wish to apply, if you was to measure differential pressure, you have to apply two different pressure sources. In this case, the pressure that I wanted to measure was applied inside the bell, and from outside the atmospheric pressure work, let us say on the outer surface of the bell or on this liquid, it was atmospheric pressure that was working. So, the movement of the bell here was the result of this application of this pressure as well as the atmospheric pressure that is working from the outside of the bell. So, in case of differential pressure gauge, we have to connect the pressure gauge to two different pressure sources. So, and I will apply one pressure inside the bell and I will apply another pressure from outside of the bell. So, that is what we do. So, what we do have to do is I have to make use of a sealed chamber. Here the chamber was open, but here I have to use a sealed chamber. So, the bell type differential pressure gauge will consist of an inverted container immersed in a sealing liquid, and the sealing liquid is taken in a sealed chamber. Now, as usual, I apply one pressure inside the bell and the other pressure you see is being applied from outside the bell. Now, these two pressures are separated by the sealing liquid. Again, due to differences in these pressures P 1 and P 2, the bell will show a movement which can be used to move this pointer against this scale. So, movement of the pointer against this scale can be used to measure the differential pressure P 1 minus P 2. So, bell type manometer can be used both to measure differential pressure as well as gauge pressure. Now, let us take a problem on well type manometer. A Mercury well manometer is to have a float in the right hand chamber. An electromechanical transducer is used to measure the motion of the fluid. The float motion is 7 millimeter for a gauge pressure of 30 kilonewton per meter square. If the diameter of the float chamber is 50 millimeter, what is the required diameter for the left hand chamber? For Mercury, density is equal to 13600 kg per meter cube. Assume that the other end of the manometer is open to the atmosphere. So, basically consider a well type manometer. We want to have a float in the right hand side chamber. So, here I want to have a float. An electromechanical transducer is used to measure the motion of the fluid. The float motion is 7 millimeter for a gauge pressure of 30 kilonewton per meter square. If the diameter of the float chamber is 50 millimeter, what is the required diameter for the chamber? So, what should be the diameter of the chamber? Density of the mercury is given. So, first let us try to find out what is H2. Given for 30 kilonewton per meter square pressure, this level of mercury in the well goes down by 7 millimeter. So, when you apply 30 kilonewton per meter square pressure, you have H1 equal to 7 millimeter. So, I can write 30 kilonewton per meter square, which is 30,000, equal to rho g H1 plus rho g H2. So, if we solve this is 30,000. So, if you solve this equation, you will get H2 equal to 0.21 meter. So, once I have H2, I can make use of the volume balance H1 equal to H2 to find out the area, and to after finding out area I can find out the diameter. So, you make a volume balance H1 A1 equal to H2 A2. So, you can write this equation. The area can be taken as pi d square by 4. So, after putting all values, we can calculate the diameter. Let us take another example on manometer. Consider the inclined manometer containing mercury as shown in the figure. Pipe A has water flowing through it and oil is flowing in pipe B. The pressure in pipe A is 10 kilopascals. Find the pressure in pipe B. Also consider the dimensions that are shown, the numbers that are put in the figure. What is given is P A is 10,000 pascals, density is 1000 kg per meter cube, its density of water, density of oil is 870 kg per meter cube, density of mercury is 13600 kg per meter cube, and H m is 9 centimeter converted to 0.09 sin 40 degree. Now, let us put all these numbers together and write down this balance. So, basically we are writing a balance along this line. So, I can write P A plus pressure due to this, which is density rho A times G times 7 centimeter, which is 0.07 meter, is equal to P B plus rho G H term corresponding to this and also rho G H term corresponding to this. Once you do the calculation, you get P V equal to 886.33 Pascal. Finally, let us take another very small example on barometer. The height of the mercury barometer is h. When the atmospheric pressure is 101325 Pascal. So, height of the mercury barometer is h when the atmospheric pressure is 101325 Pascal. Let us try to calculate the pressure at point A. Is given that this distance is 2h by 3 and this is h A. Atmospheric pressure is equal to rho G H is given as 101325 Pascal. H A is h minus 2h by 3 is h by 3. So, pressure at P A is due to this column of mercury. So, H A is h by 3. So, h by 3 into density of mercury into acceleration due to gravity, which is rho G H by 3, rho G H is this term. So, 1/3 of that is equal to 33775 Pascal. So, we will stop our lecture 22 here.